Disclaimer. This course is not a course on foundations, so I shall not be citing the axioms and I shall not be talking about the primitive notions. I shall just proceed assuming that you are familiar with the basic facts about elementary Euclidean geometry. So you will know what a line is, what a point is, what an angle is, what circles are, conic sections are, so on and so forth. Yet there will be situations where I shall make small, short, brief interludes where I shall be correcting certain well-established misapprehensions. So certain things which are traditionally misunderstood, I will stop and correct them. But apart from that, I assume that you are familiar with the basic notions of geometry, elementary plane Euclidean geometry. Right. And that's not too difficult, in fact, to do, because almost everything that I shall do this term will be based upon two very ancient observations, usually attributed to Thales. Okay, so I shall try to make a habit of writing and pronouncing the names of Greek mathematicians as close to their original form as a Turkish pronunciation allows me to do, because I really hate this French and English attitude of deforming Greek words and pronouncing them in a funny way. So, Thales. And, well, you are familiar, but just learn them, okay? I think this is the least that we can do to a nation who has produced really wonders in the subject of geometry. Thales. So, two results which are, as I said, traditionally attributed to Thales, and he has lived really very early, so somewhere near minus 620 until minus 545. Okay, so that's Ionia nowadays, our territory. Fine. Anyhow, essentially the observation which we attributed to Thales. Well, so let me call them theorems attributed to Thales. Well, the first one is essentially about proportions of line segments. Well, essentially it boils down to our basic knowledge of similar triangles. It goes like this. When you have two straight lines, and I would like to take them as straight lines which intersect, okay, rather like this, and suppose that they intersect, let's say, in a point O. And let me choose points, well, I think what I'm trying to say will be quite clear, yet let me do it by choosing 4 points on the one straight line. Let me call this straight line K, and the other one K prime. Okay, so, and then let's draw parallels through A, which will intersect K prime and A prime, B prime, C prime. It's not easy for me to put pictures on the blackboard. You know, when we are looking at objects from this perspective, you may sort of fail to draw parallel lines, etc. Anyhow, so parallel lines A prime, B prime, C prime, D prime. Let me take another one just for purpose of illustration of a certain point. And let's say Z1, Z prime, okay, ZZ prime, AA prime, BB prime, CC prime, DD prime, ZZ prime. Okay, so what Thales has observed that if you take the ratio of, let's say, BA, AB, let's say, to CD, that ratio is exactly the same as A prime, B prime, C prime, D prime. Now, there are a few things I will say about this ratio, what exactly it is, because we shall charge it with a meaning slightly more convoluted than the one that you learn at primary school. Okay, so there is something which I wish to say in a minute about these ratios, and also he observes that about the distance from the origin, let's say for instance OA to OB, the ratio OA to OB is of course the same as OA prime to OB prime because of this as a special case. Yet, furthermore, this OA to OB is exactly the same as AA prime to BB prime. Now that also needs some explanation. I shall do that in a minute. So this is essentially what Thales observed. And you know, there is all this is sort of the heroic age of geometry. We don't know much about Thales himself. Very little is known, and it's really a bizarre twist of fate that we have got this rather accurate knowledge about his birth and death. That's another thing. But about him, we know little. But in the West and in the East, he is a very famous ancient personality. He's counted among the so-called 7 wise men. That's just as we say in Turkish or Turkified Arabic, hükemâ-i sitte. Okay, so one of the 7 wise men. Okay, so he's almost a mythologic personality. We know very little about him, but these two relations survive. Of course, he never wrote them down like this, because actually in those days they did not know zero, they did not know negative numbers. And talking about negative numbers, okay, so what do I mean by an expression like this? Well, this is of course the ratio of the length AB to the length CD, if you wish. Yet I wish to understand it as a directed quantity. So I shall assume that this quantity is a positive quantity if AB and CD are pointing in the same direction. If not, I will understand this to be a negative quantity. Okay, so that's rather. And in fact, you can. So let's turn to modern mathematics. So you can actually define this exactly. This is the quantity lambda, a real number, where you can understand that the vector AB can be written as a multiple of CD, and that factor is exactly lambda. Okay, so that is explanation enough. So let me make that absolutely clear. It's of enormous significance that this quantity should be a signed quantity. We shall soon make use of it in a vital fashion, and it is one of those concepts, well, mainly because of the stupid cramming schools which you have to visit before coming here. One of those objects which are very badly misunderstood. Okay, so I'm stopping and making remarks about this. Okay, so let me give you some examples. For instance, well, if you have got, let's say, P, Q, and R like this, and let's say this is 4 units and this is 7 units. So if you wish to write, for instance, the ratio PQ to QR, for instance, that's obviously going to be 7/4. Whereas, if you wish to write the ratio PQ, okay, so let's do it, PQ to PR, that is going to be 7/11. And finally, for me, the most important one, if you want to write the ratio QP to QR, that is going to be minus 7/4. Okay? So please note this. That's going to be of vital importance. Okay? Right. So that is one result that is traditionally attributed to Thales. Another one, okay. Okay, another one, which is in its basics, in its essence, should be familiar to you. It is merely the observation. Okay, so that's it's merely the observation that the angle subtended by a constant arc on a circle is independent of the point on the circumference. So let me make this absolutely clear. So if you take a circle, now this is another thing which I find very difficult to draw, and okay, and let's say you have got 2 points on it. Let's say A and B. Now you can imagine, so for any point x, you can talk about the angle subtended by the arc at the point x. Okay. Okay, so observe the way I'm making it absolutely clear that I'm not talking about line segments, but I'm talking about lines. I do that by, for instance, when I'm joining the points A and B, I don't stop at A and I don't stop at B. I sort of go a little bit further to indicate that I'm talking about a line, not a line segment. For instance, in this case too, this is the line XB, and this is the line XA. Okay, so you can measure the angle between XA and XB. Now there are 1 or 2 things which I have to say. And if you change the position of Y, and if you repeat the same process, okay, so the angles, okay, let me call them 1 and 2. The angle 1 is the same as the angle 2, okay? And of course, Thales has also noted, in fact, this is the part which was most frequently used in those days, and if the arc we talk about is actually the endpoints happen to be the endpoints of a diameter. Okay, so this is the center of the circle. If this happens, then the angle subtended at any point on the circumference, like this, okay, is in fact 90 degrees. That's fixed. That's pi/2 if you are measuring in radians. It's 90 if you are measuring in degrees, which I shall never do. Well, I shall occasionally do. Okay, never mind. But right. So these. Okay. So I will base everything. I will base everything on these 2 observations, and of course their ramifications. Okay. So, right. And so just as I have talked a little about these ratios being signed quantities, I have also a few things to talk about the angle concept. Well, that's rather difficult, but I'm not going to talk about it as yet. So it is this thing. So it's the angle that I have called 1 is equal to the angle that I have called 2. Now you can use the following notation. That is the angle. Okay, so the 1 is the angle between the line AXA and the line XB. Now observe the curious way I am talking about the angle between lines and not about half lines or rays. Now that's going to be an issue, and I shall take it up. I shall take it up soon. I don't want to spoil your joy by going into those details, technical things right now, but this will be, I shall make an issue of it. So that's, how is this angle defined? So this is, so let me mention the thing. This is an angle between lines. And make my meaning absolutely clear by putting the adjective undirected. Now this is something important, and I shall address this issue soon, and in fact many times, but later. Let's for the moment take it as given. Right. So with this introduction, now I can pass on to my first topic, which I like to call basic features of the triangle, because you see, there are several things which I shall be trying to clarify in this course, and whatever those may be, they will be mostly done by means of the triangle, mostly be done by means of results about the triangle. So here is my first subject, 1. Well, I like to call it basic features. Basic features of, well, the classical triangle. I shall leave it to you to judge how appropriate such a title is. Okay. First, I would like to talk about a very simple fact. Okay, so let me do it on this part of the blackboard. If you take, let's say, a line segment, AB, and if you find its midpoint, let's say M, and if you erect a perpendicular at that midpoint M to the line that joins AB, so this is not only the midpoint, and this line not only passes through the midpoint, but it's also perpendicular to the line segment AB. Well, this thing is called the perpendicular bisector. The perpendicular bisector. Now that's perpendicular bisector. This should be familiar to you. Perpendicular bisector of, please note my notation. I shall be rather particular about this notation. I shall frequently have a comma in this part, but not always. Okay, so the line segment AB. So the perpendicular bisector. Now that's an important expression. Now what is spectacular about the perpendicular bisector is the following. If you take a point, any point in fact, let's say P, on the perpendicular bisector, then you can easily show that the distance PA and the PB, they're equal. So these two line segments are equal in length, or they are congruent if you wish. And this happens for any choice of points. And conversely, in fact, so if you choose P prime, okay, P double prime, keep an open mind. It's any point on the line segment. Okay, so it's I don't know. And in fact, this straight line, which I have called perpendicular bisector, is exactly characterized by this property. That's to say, the perpendicular bisector is in fact exactly the set of points which are equidistant to the two extreme points of the line segment, right? So that's a very simple thing. Now, let's apply this to the triangle. If you take a triangle, well, I shall be, okay, here is another one of my pet aversions, my dislikes, one of my strong dislikes about habits which you have brought to us from the cramming schools. Do not ever draw an equilateral triangle. When I ask you something about triangles, try to make your triangles as generic as possible, okay? Because you see, when you take okay, so people say, let's take a triangle. Okay, don't do that, okay? Not only it gets on my nerves, but it's totally the wrong attitude in this subject, okay? So it heralds really a bad future. So try to draw a triangle which is, what was the word, as generic as possible. So not two sides coinciding in length, angles not coinciding. So try to make your triangle look as general as possible. Allow no coincidences. So, I don't know, it's a matter of taste, but I really take something rather like this, okay? And in fact, whatever you do, try to imagine how that would look like with different kind of triangles. So try to keep your mind open. Okay, so the triangle ABC, I shall also be paying attention to the way I choose my notation. Okay, so for instance, ABC in this counterclockwise fashion. And let's take the perpendicular bisector of the side of the line segment BC. So let me start with the midpoint of the line segment BC. So these two line segments are equal in length. So I've started with the midpoint. Now let me do the very same thing with the other sides. So let me take the midpoint of C and A, and what do you think I should call it? Me doing everything in cyclic fashion, going counterclockwise around my triangle. Since I have called the midpoint of BC A prime, I shall call it B prime, and I shall repeat the same thing with the line segment AB, calling it C prime. This isn't just this. You may think I'm a fatty person, so I'm not doing it just because I like it. I'm not paranoid or something, but it helps. You will see it actually that it will help you, this careful choice of notation. Right, okay, so and then you take the perpendicular bisector at A prime of BC. Okay, so that's the perpendicular you erect to B side BC at A prime. And you take the perpendicular bisector at B prime, and well, what do I know? I know that the perpendicular bisector of the line segment BC consists exactly of those points which are equidistant to B and C. So whenever you take a point, its distance to B is equal to its distance to C. And with the line segment, with the perpendicular bisector of line segment CA, something similar happens. Whenever you take a point on this line then its distance to C and its distance to A, they are equal. So these two perpendicular bisectors in fact intersect. And ask yourselves, why? Why do they intersect? Isn't it possible for two such objects not to intersect? Well, that would be rather silly. you know, in Euclidean geometry, if you want two lines not to intersect, they must be parallel. Well, if they are parallel, then they cannot be perpendicular to two lines which are not parallel. And I'm tacitly assuming in my triangles that none of the angles reduce to zero. Okay, so, but, well, this is not one of our concerns, but there are geometries, not quite like Euclidean geometry, but close to Euclidean geometry. Very close, the so-called Lobachevskian geometry or hyperbolic geometry, in which such two lines, such two perpendicular bisectors may fail to intersect. I mean, you may have something like this. Perpendicular bisector going like this, perpendicular bisector going like this. But that is a different kind of geometry, not Euclidean geometry. Okay, so in our geometry, there is no problem. Okay, so let's call the point in which they intersect O. And notice that the distance of O to B is the same as its distance to C, because it is on the perpendicular bisector of the line segment BC, and because it is on the perpendicular bisector of CA, the length of OC is exactly the same as OA. So it means we have found a point which is equidistant to all three sides. Now this tells us that when you take the line segment, when you take the perpendicular bisector of the line segment AB, then that perpendicular bisector must also go through O. So three perpendicular bisectors, perpendicular bisectors of BC, the line segment BC, CA, AB. Okay, here is an expression, here is a word, here is a piece of terminology which I would like to teach you. So you can also, of course, say, using a very simple language, that these three bisectors go through the same point. You can also say are concurrent. That's a beautiful word. Concurrent, that means they go through the same point. And the point of concurrency is O. This point is called the circumcenter. So these are really very traditional words, and unfortunately you have to learn. I hope you are a person who takes delight in learning new and strange words, circumcenter, and let us notice something very simple. How much time have I left? Yeah, I've got enough time. Let's notice something very simple now. Well, it's really sitting right in front of us, because you see the distance to three vertices, that's OA, OB, and OC. They are all equal. So it means that if you take your compass, okay, your pergel, if you apply the point to the point A, and if you take the writing point to the point A, and if you draw a circle, then it will actually go through C and B and A. So in fact, it means that whenever you have got a triangle, then you have got a circle. You've got a circle which actually goes through the three vertices. It is very difficult to put a circle through 3 points. I mean, when you're on the blackboard. So I'm doing this fuzzy circle thing. Okay, so now I can make it a little bit nicer. Okay, so I take great delight in producing good pictures as far as I can do it. I'm not a great draftsman, but with one or two tricks, and especially if you know the geometric hinterland, then you can produce reasonable pictures. Okay, so that's, I'm sorry, that looks terrible. That looks terrible. Okay, but something rather like this. Okay, so anyhow. Right. So this thing is called the circumcircle. Circumcircle. Well, these are all pretty well-established terminals. Circumcircle, so its center is circumcenter. I've made a terrible job. Anyhow, let's, okay, so something like this. So, and observe that, okay, so these three, so the length OA, the length OB, the length OC, these are all equal. So let me, I'm terrible. Okay, so that's OA, OB, OC. So this length, this length OB, which is equal to OC, and it's OA. This is, of course, the radius of this circumcenter, and it is traditionally denoted by R, big R, okay? And this, of course, is called the I mean, you are surprised, aren't you? Circumradius. Circumcircle, circumcenter, circumradius. Right, there it is. So that's the first thing which I would like to observe. So that's something remarkable. I'm not quite sure about the history. I'm never quite sure about the history. In fact, nobody is quite sure about the history. But this sort of construction appears to have been known to mankind since very ancient times. Almost every civilization has something like this. And anyhow, this point O is a rather remarkable point. And I shall spend the next hour producing the best known, the most traditional, remarkable points about the triangle. So an alternative title for my talk is the 4 remarkable points. Well, of which I've got one. Okay, so the first remarkable point happens to be O, the circumcenter, the point which is the center of the unique circle that goes through the 3 vertices. Now, okay, so allow me at this point to point out one thing. In geometry, you know that if you take 2 distinct points, then you can draw a single unique line through those 2 points. Now, we have learned that if you have got 3 points not on the same line, then you can draw a circle through them. There is nothing extraordinary about this, okay? So that is rather, okay, that's about it. So that's the first remarkable point. And as I say, this sort of thing has been known to almost all sorts of civilizations for a very long time. Now let me introduce yet another interesting point. Okay, here is the thing. So that's my first thing. Okay, let's take a triangle. Once again, I'm trying to take as generic a triangle as possible. Some people criticize my triangles because they say it looks a lot like an isosceles triangle, despite all your, okay, so there it is, ABC. Now, let's look at the altitudes. That's to say the perpendiculars that you drop from each vertex onto the opposite side. For instance, take the point A, and let's drop a perpendicular from A onto the opposite side BC. Okay, so that's simply a straight line which goes through A and it's perpendicular to BC, right? And then you can, okay, so let me not draw the whole thing. And we can also draw similarly an altitude through B, that's to say a perpendicular to the side CA going through B. and you can drop a perpendicular from C onto AB. Let me draw them together. Okay, şimdi çocuklar, I think you are now familiar with the kind of thing I am crazy about. I like to take 3 lines and I want to show them that they all go through the same point. Okay? So in Euclidean geometry, if you take 2 lines, unless you are unlucky and if they are parallel, then they intersect in 1 point. There is nothing extraordinary about it. If you take 2 lines, they intersect in 1 point. But if there are not 2, but 3 lines going through the same point, then it's the situation, it's a circumstance under which the geometer person sits back and takes notice. Okay, so this is, I mean, if you are that kind of person, you should go on with this course. But if you say, I mean, what the hell, I mean, what do I care whether they go through the same point or not, then this course is not for you, okay? So it's apparently you should be interested in other subjects. Anyhow, so I would like to see, for instance, that they go through the same point. Do they or they do, they do or they do not? Let's see. Now, this can be shown actually in many different ways. By the way, you can do it very nicely. I wish I could show you ahead time using vectors, for instance. That 3 altitudes go through the same point. It can be done very nicely using vectors. But I would like to do it in elementary fashion. So I have to use a bit of a trick. So I pull some things out of my sleeve. And those things are the following. Let's draw a line parallel to the line BC, to the side BC, through the point A. Okay? And as you may have noticed, I have drawn this triangle a little small, not too large. And let me take a line parallel to AB through the point C, like this. And let me take a line through B parallel to CA. Now I have obtained a triangle. Which is rather remarkable. Okay, so let me call, for instance, this triangle. Okay, so let me call the vertex sitting opposite A. Well, for reasons to be disclosed later, let me call it GA. And let me call this GB. Observe once again my cyclic notation. It's always a very good idea to keep track of things. You choose your notation carefully. Okay, fine. Now you can easily check that actually these 4 triangles are simply replicas of the ABC. And in fact, for instance, this length BC and this length are equal. In particular, A is the midpoint of GBGC. So on the other hand, the altitude through A, on the other hand, GBGC is also parallel to BC. Where do I get this, çocuklar? It's the theorem of Thales. In fact, theorem of Thales works backwards. In fact, you can also say that. Okay, so if these lines are parallel, you have got these identities, and if these identities are there, then you must have parallel lines. Okay, so I possibly forgot to mention that. Okay, so I know that the line BC is parallel to GBGC. So if you take an altitude, that means if you drop a perpendicular from A onto BC, it is also perpendicular to the side GBGC. So the altitude through A, the altitude in the triangle ABC through A is in the big triangle GAGBGC. The what? It's the perpendicular at the midpoint. The altitude through A in the triangle ABC is in the big triangle GAGBGC exactly the perpendicular bisector. You see that? This is rather important. This GAGBGC is, for all practical purposes, the same as ABC, except that it has been pulled apart to assume twice the proportions, and it has been turned upside down. You get that? The same triangle, multiply by 3, 2, and turn upside down. It's exactly the same thing. And the curiosity is that the altitude through A is the same as the perpendicular bisector of GBGC. Okay? So I know that perpendicular bisectors intersect in one point. So simply notice the altitude through A in ABC is the perpendicular bisector, check that I'm abbreviating PB, perpendicular bisector of the line segment GBGC. So from this, I come to the conclusion that altitudes, 3 altitudes, in ABC concur. Check that this point, okay, so let me make a picture. Let me make it a little bit more attractive. So your point, the point that I'm talking about, the point in which the 3 altitudes, here they are, this altitude, and this altitude. These 3 altitudes intersect in one point, and that point is traditionally denoted by H. Just as the circumcenter is traditionally denoted by O, it's denoted by H, and it's called the orthocenter. The orthocenter. The orthocenter. Okay, and okay, so well, actually, well, there are some interesting. There are quite a lot of interesting stuff to be noticed. You can actually, okay, so you can look. You can, if you wish, let's denote by the foot of the perpendicular of the altitude through A. Let's call it A tilde, and let's call the foot of the altitude through B tilde and C tilde, as usual in cyclic fashion. So, for instance, the length, okay, so the length AA tilde, the length of the altitude is traditionally denoted H sub A. Now, this is something important, and similarly you can define the lengths HB, HC, and of course, this is known that the area of the triangle is actually twice the area of the triangle is A times. Okay, so these are traditional notations. So let me show you, and let's be over and done with. HB equals CHC. Okay, so what's A? A is of course the length of the side BC. B is of course the length of the side HCA, and C is of course the length of the side AB. Right, there we are. So this is about the thing. So these are well known, and this gives us the second remarkable point, which is H. Now we have got once again. Let me repeat the same. Let me repeat the same observation. These points have been known to all kinds of civilizations since very ancient times. It is very dramatic, actually, as you shall see in a minute. There is one observation which I would like to make about these quantities. So that's very simple. That's ilkokul, actually, something that you have known for a long time. So let me make this in the form of a remark. And in fact, this is a leitmotif. We shall come back to this remark, and in fact, similar remarks. You see, B times HP is equal to C times HC because both of them give you the area. So if HP is equal to HC, for instance, so if two altitudes have the same length, then you must conclude from this formula that B is the same as C. So in fact, well, B is of course this length. So let me use this triangle. So this is the length B, this is the length C, and this is the length A, if you wish. Okay? So in fact, it turns out that your triangle must be isosceles. Well, that sounds like a rather trivial observation, but I must ask you to wait. Now this is to be, I shall come back to this, to be revisited. I shall come back to this. Okay, now I have filled up the blackboard, and perhaps it might be a good idea to stop here. Let's take a break, 10 minutes.